All right, class. So now we are in section 8.4, and we are learning about convergence tests. We want to know, a series, of course, is when you take the terms of a sequence and add them. So you're adding an infinite number of terms of a sequence, and you want to know if that summation, that series, has, or we sometimes call it an infinite series. We want to know if the series has a finite sum. If it does, then we say the series converges. Now, we've learned some series in section 8.2. Some very common ones are geometric series and harmonic series and telescoping series. And then in section 8.3, we talked about some series that were less familiar to us, but nevertheless, we can analyze if the series converged or diverged by virtue of some new tests, like the integral test and the comparison test and the limit comparison test. Now, for section 8.3, those tests are for the series in section 8.3 are series where all the terms are all positive. Okay, they're all positive. But what if we had a series where the terms are not all positive? In other words, some terms are negative of the series and other terms are positive of the series. That's what we're dealing with in section 8.4. So right there in the beginning, it mentions for this other convergence test, section 8.4, the convergence tests that we have looked at so far apply only to series with positive terms. In this section, we'll learn how to deal with series whose terms are not necessarily positive. So let's go right away to one of the common tests here. One moment. Well, let's look at a couple of common series here. So here, they talk about a series called an alternating series. An alternating series. So take a look at these two series that you see here, and maybe I can highlight them. Okay. So these are called alternating series. So look at the first series. The first series, 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. And there they write out the series formula on the right. And you see how that they have the numbers, the terms resembled the terms of a harmonic series, right? But the terms go positive, negative, positive, negative, positive, negative, and so forth. And so you need the -1 to the n minus first power so that you can get that behavior. The second series as well is an alternating series. Okay, so a question that comes to mind, and maybe I'll put this on the whiteboard. Okay, is the following. Make a note here. Okay, so the series 1 plus a half plus a third plus a fourth plus a fifth plus a sixth and so forth. We know the formula for that series. What kind of series is this? What kind of series do we have? What is this famous series called? That's right, nothing else. It's a harmonic series. And does a harmonic series converge or diverge? That's right, Javier. It diverges. Sorry. One moment. One moment. All right, sorry about that, class. Let me go ahead and put my this phone on silent. Let me do that right now because I don't want uh, 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 phone calls um, interrupting our lesson here. So hold on, let me just put it on. Let me put it on silent. There, that way if it rings, well, I have two phones. I have my cell phone. That was my cell phone that rang, and then I have the house phone. But the house phone, all I ever get is just I could just hang up on those phones because they all they want is money, right? These telemarketers. So all right, let's continue here. So harmonic series, and that's correct, class. That diverges. Now let's look at another series. Let's look at 1 minus a half. And you just saw this series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. So this almost looks like a harmonic series, except the fact that the terms are alternating from positive to negative. So sometimes we call this an alternating harmonic series. And an alternating harmonic series, just one moment here, an alternating harmonic series actually converges. So the fact that some of the terms are negative affects the series and the fact that it will converge. So this is a very sort of a fascinating idea here. The harmonic series diverges, but if we have the alternating harmonic series, that converges. Now, we have a test called the alternating series test that we can use to show this. One thing I'll mention here is that you know, well, let me go to the alternating series test, and then I'll come back to this. Okay, so let me go back to the ebook. Here's the alternating series test. And what it does is it expresses an alternating series in a general form. Okay, maybe let me just see here. Maybe just take out. Hold on, everybody. Yeah, this is good. So this is the general form of an alternating series. So the b sub n term is like the absolute value of each term. All right, and if that alternating series meets the two conditions below, then the series converges. So the first condition says that b sub n plus 1 is less than or equal to b sub n for all n. That just means that the terms of the series are decreasing. Okay, now we're not considering the plus or minus part. We're just considering, the absolute value of each term. But the terms of the series are decreasing, and the second condition is that the terms of the series approach zero. So, a harmonic series satisfies both of these conditions, but the harmonic series is not an alternating series. But the alternating harmonic series satisfies both of those conditions, and that's why that series converges. So if I were to go back to the whiteboard here, where this alternating harmonic series is, okay, let me just hold on here, move this over. Okay, hold on, let me put it in red. Yeah, let me just kind of separate things. Here's the alternating harmonic series. Okay, so 1 equals b sub 1. A half equals b sub 2. A third equals b sub 3. A fourth is b sub 4. A fifth is b sub 5, and so forth. So you can see that the n plus first term is less than or equal, well, it's less, but it's less than or equal to the nth term. That's the first condition of the alternating series test. In other words, the b terms are decreasing with n, and also the limit as n approaches infinity of the nth term is equal to 0. The terms are dying down to 0. So that's enough. So to say by the alternating series test that the alternating harmonic series converges. Okay, are there any questions on that? Okay, let me go back to the book then, one moment. Bring up the ebook here. Okay, so we use the alternating series test to do this, and the reason the alternating series test is true, they give an intuitive idea here in Figure 1. What they do is they basically add terms of an alternating series and then look at the partial sums. So the first partial sum is just the first term, b sub 1. The second partial sum is b sub 1 minus b sub 2. That gets you over to the second partial sum over there on the left. And then if you add b sub 3, which is smaller than b sub 2, that gets you the partial sum s sub 3 on the right. You know, every term you're adding or subtracting gets smaller and smaller. So what eventually happens to the partial sums is that they congregate around that center value s, and so s would be a limit of this sequence of partial sums, and so that's an intuitive idea, an intuitive picture of why the alternating series test works. And I think let's go ahead and look at a few examples here. So let me bring up a few examples. Okay, so now the first example we actually did already, but nevertheless, we'll formally have it here in the notes. Let me give you a moment to copy these examples down, and then we'll discuss them. We'll discuss their solutions. Okay, give you another minute here to copy these down, these examples. We're trying to do a variety. because you have to be very careful with the problems in these in like sections 8.4 and 8.3, because a lot of them are where does the series converge or diverge, and it's like a multiple choice question. You have one chance to get it right, so you really have to kind of take your time, right, on those problems. All right, so the first problem, let me just move this. Yeah, the first problem we've already done. So let me show you the solution for the first one. That's the alternating harmonic series. And, this is, if I wanted to be very formal, this would be the solution. So the B sub n, well, let me go back here. Hold on. Let me go back. Let me just be a little more. So 1 is B sub 1. A half is B sub 2. A third is B sub 3. A fourth is B sub 4. Okay, and it's clear that the B sub n is 1 over n. So if we look now at the alternating series test, okay, in the solution, B sub n naturally is 1 over n. And the first condition is satisfied. B sub n plus 1 would be 1 over n plus 1. That's less than 1 over n, which is B sub n. So that just is a fancy way of saying the terms of the series decrease in absolute value. And then the second condition, of course, is that the terms have to go to 0. And by the alternating series test, our series, this alternating harmonic series, has to converge. Please let me know if you have any questions. Okay, so I think you're good with this. Let's go look at the second series here. Look at this series here. Now, is the series in B, let me just get my pen. Is this series in B, is this series an alternating series? That's right, Ange. It definitely is, because you have you have this -1 to the nth power in there, and that causes the series to alternate between positive and negative. So as n gets large, remember, whether a series converges or diverges depends on how the series behaves as we move out into the series. As we look at terms later and later in the series, how do those series behave? So when n is large, is the -1 here going to matter much in terms of the value of the terms of the series? Does that -1 affect the values much? That's right, Javier. That's right, Taj. It does not. So essentially, you could almost think about ignoring the -1 and saying, okay, the series will eventually behave like a series where you have 3n divided by 4n. What's 3n divided by 4n? 3/4. That's right. So what do your instincts tell you about this series? Do you think this series is going to converge or diverge? That's right, Ange. It's definitely going to diverge because the terms of the series are not approaching. That's right. That's right, Tosh. The terms of the series do not approach 0. Now remember, in general, just because the terms of a series, if they do approach 0, that doesn't mean that the series is going to converge. Harmonic series, for instance, that series diverges, and those terms approach 0. But certainly, if you have a series whose terms do not approach 0, the series has to diverge. And really, what we're using here, what we're using is the test for divergence. That's really what we just used here. So, and also we can further say that even more than that, the limit of the terms doesn't exist because yes, the 4n, the 3n divided by 4n is 3/4. But don't forget, you have the -1 to the nth power in there. So the terms of the series are going to oscillate back and forth between positive and negative. And so the limit of the terms of the series does not exist. So the series has to diverge. Effectively, as n goes to infinity, the terms of the series are behaving like 3/4, -3/4, +3/4, -3/4, +3/4, and so on. The series never converges. Please let me know if you have any questions on that. Let me give you a moment to copy this down. While you're doing that, let me just see how Sensar, how do you feel about that? Are you comfortable with the explanation behind why this series diverges? Okay, good, excellent. Ethan, what about you? Do you feel comfortable with this explanation? Good. And you know, I add in a few of my personal notes. Just I'm trying to kind of help you develop an intuitive feel for these series. So I try to add in sort of intuitive explanation. Do you find this extra intuitive explanation helpful here about how the terms, like how the series eventually behaves as like 3/4, -3/4, +3/4, -3/4, and so forth? Okay, Ange likes that. That's helpful. Oh wow, great. Ethan and Jan as well. All right, wonderful, wonderful. Okay, okay. So let's now, if we're good with this, let's go ahead and look at the third series. So the third series here in this problem we have the series, let me just put it, where we have the cosine of n divided by n squared. And naturally, we would want our calculators in radian mode when we compute the terms, but they're the first three terms. Is this series a alternating series? Could we say this series is an alternating series? Well, the cosine is periodic. I'll tell you what. Let's compute a few values. Let's compute a few values. Oh wait, now nothing else says it's not alternating. Nothing else says the series is not alternating. Well, I can tell. I mean, I'll tell you what. Let's go ahead and look at the solution on this and see why the series is not alternating. Okay, it'll be easiest just to go right there to the solution. So what I did was I computed the first, well, I mean the cosine of one. So let me just say this the right way. The terms of the series are cosine of 1 over 1 squared plus cosine of 2 over 2 squared plus cosine of 3 over 3 squared, and so forth. So the denominator is always positive. So it's these numerators here that are going to determine then the sign of the terms. And the first term, cosine of 1, is 0.5403. So the first term is positive. The cosine of 2 is negative 0.4161, so the second term is negative. But the cosine of 3 is negative 0.990, okay, which is negative. So this series, it turns out in the beginning, it was alternating series, but now it's not. So this is not an alternating series. And therefore, we cannot apply the alternating series test. Okay? Because it's not an alternating series. So we have to try something else. One moment. Well, that is right, Ange. We want to work off using the comparison test. But remember, the comparison test only, and you learned that in section 8.3, that's for a series where the terms are all positive. Now the series that I'm interested in, right? The series that I'm interested in is this series. Right? That's what I want to know about. But what I can do is look at this series here, where I take the absolute values of all the terms. Okay, we could look at that series. And let me ask you this. Let's call this series 1. If series 1 would converge, would series 2 converge? Okay, and that you're right, Ange. If this series here converged, where we have the absolute values of the terms, if that series had a finite sum, then the series we're interested in would also have a finite sum. And why is that? Which series has a larger sum, series 1 or series 2? That's right, Javier. That's right, Ange. Series 1, because all the terms are positive of that series. So we're using a concept that we call absolute convergence here. We study the series if all the terms were positive, and if that series converges, then the series without the absolute values on the terms would also have to converge. So what we do, okay, well, this cosine of n over n squared, again, the absolute value of the cosine of n over n squared, the cosine of n is always less than or equal to 1. So the absolute value of the cosine of n over n squared is less than or equal to 1 over n squared. Okay, and the series 1 over n squared is a convergent p series, right? Because p equals 2, which is greater than 1. And so therefore, the series where the terms are the absolute value of the cosine of n over n squared, that series would have to converge by the comparison test. Because remember that by virtue of the inequality, I might have to, hold on. I need a little more space here. Let me write it nicely. Gosh darn it. Hold on. That series is less than, or, well, it's actually straight, it's less than, right? It's less than our P series, right? By virtue of the fact, by virtue of this inequality here. So therefore, if our P series converges, then this series here has to converge, right? That's the idea. And now what can we, so what do we say then? What do we say? What we say then is that our series here, the series that we're interested in, that series is absolutely convergent, and so it converges. Okay, so that's an absolutely convergent series. If the series converges, absolutely, then the series converges. Okay, and that's how we would do a problem like that one. Hold on. Ange says the harmonic series actually, Ange does, okay, Ange's, your question about the harmonic series actually does not absolutely converge. Okay, so like here, well, no, actually, hold on. We're talking about the alternating harmonic series, right? Right, so this is the alternating harmonic series. But if we, which converges, but it does not absolutely converge, because if we take the absolute value of the terms of an alternating harmonic series, that would give us this series, which is the harmonic series, and that diverges. So we can't use absolute convergence to establish that an alternating harmonic series converges. But we do know by the alternating series test that the alternating harmonic series converges because its terms satisfy the two conditions of the alternating series test. All right, so that's a good so this is not what I wrote below here is just answering Angie's good question, but but our solution to part C ends here. Are there any questions before we look at a few other ones? All right, let's go forward then and look at a few more examples. So yes, Elmer, question? Want me to go back here? Okay. Okay, well then let's proceed on here. All right. So here are a couple more series that we want to see if they converge or diverge. So let me give you a moment to copy these down, okay? Okay. Okay. So um, the uh, the first series here, what does the 4 to the nth power in the denominator kind of remind you of? What does that series kind of remind you of? That's right, Ange, a geometric series. So sometimes when you look at the series, uh, you might relate it to something that you've seen before, and that gives you a clue on how to analyze it. So what we're going to do here is we want to involve a geometric series, but we have this series, the sine of 4n divided by 4 to the nth power. What if we were to look at the absolute value of the terms? Okay, in other words, what if we were to consider this series here. Okay, what if we were to, hold on here. Let me just, what if we were to consider this series here? This series here is going to be it's going to be easier to analyze because all the terms of that series are positive by virtue of the absolute values. And we could use maybe the comparison test. That's right, Ange is already thinking it. So let's go to the solution. Here's the solution. Okay, so this is the solution. So, okay, the absolute value of the sine of 4n divided by 4 to the nth power has to be less than or equal to 1 over 4 to the nth power. The sine function, the sine of any angle, is always bounded between -1 and 1. Now, 1 divided by 4 to the nth power is equal to 1/4 to the nth power. And so, all right, we recognize the series n equals 1 to infinity of 1 to the 4th to the nth power as a geometric series that has a common ratio of a fourth. And it's convergent because the absolute value of a fourth is less than 1. Therefore, by the comparison test, the series n equals 1 to infinity of the absolute value of sine of 4n divided by 4 to the nth power, that has to converge. Well, this means then our series converges absolutely and therefore converges. Let me give you a moment to copy that down and let me know if you have any questions. So sometimes I like to just kind of complete my thought, you know, and then let you copy it down. Okay, let me know if you have any questions. Who's feeling good so far with this material? Who's feeling reasonably okay? Javier's okay, and Jan's all right. Okay, you know, just trying to keep it. Ange is okay. Good. And you know, we're just trying to sort of use our intuition here. We have to be a little careful with series in regards to intuition, but this seems very um, uh, uh, understandable. Now let's look at this other series here. Let's look at this other series. If you're good with this one, let's look at the other one. okay, the series here in B. So this series here in B, this is an alternating series, right? Because you have a -1 to the nth power, and you have n, and then times n cubed over 3 to the nth power. Now, would the alternating series, so let me ask you this. Let me clear this. So I'm focused here on B. So B sub n is n cubed over 3 to the nth power, and you know, one of the if we were to try to verify the first condition of the alternating series test, we'd have to show that the b sub n plus 1 is less than or equal to b sub n. In other words, what we'd have to do is we'd have to see if n plus 1 actually, hold on, let me write this below here. I forgot, I got space below here. So here's b, okay. So b sub n for b is n cubed over 3n. So if we were to use the alternating series test, we'd have to show that the n plus first term is less than the nth term. That's one of the conditions that we would need to verify. In other words, we'd have to show that n plus 1 cubed over 3 to the nth is less than or equal to n cubed over 3 to the nth. Okay. Is that easy to show? Is that easy to prove? Do you think that's easy to show for this series, that the terms are decreasing? To show in general that I mean, like for the alternating harmonic series, it was, you could almost just by, you know, like it's intuitive looking at the terms that those terms are decreasing with n. But now we're trying to see if these terms here, in this series, you know, the n cubed, like this part here, we're trying to see if those terms decrease with n. Is this something that is easy to show? What do you think? Yes or no? Well, you know, Taj, Taj is saying 3n goes to infinity. So yeah, Taj, you're saying, and your input's good, it should be the case, but you know, it's not easy. It's not, I mean, if we were to mathematically prove this statement, it's not, you know, easy to prove. I mean, it might not be so easy to prove. Rigorously showing it would be hard. That's right, Taj. And because of that, I'd like us to use another test. It's an alternating series, but the alternating series test would be rather difficult to use here. So we're going to use a test called the ratio test. And what I'd like to do is I'd like to bring this test up for you. Let me do that. Let me bring up the ebook. Okay, this is the ratio test. This is the ratio test. And let's look at the test here. What does it say? So it's saying, look at the ratio of a series. Look at the ratio. I mean, let me just see here. Let me highlight the first part here. First series, take the n plus first term and divide it by the previous term, the nth term. Look at that ratio and let n go to infinity. Look at that absolute value of the ratio of the n plus first term of the series to its previous term. Let n go to infinity, and if the absolute value of that ratio equals some constant L, and L is less than 1, then the series absolutely converges, and therefore is convergent. On the other hand, for part B, okay, for that part, maybe I'll actually do it in pink. There it says, look at, again, the absolute value of the ratio. Let n go to infinity, and if that limit equals L, which is greater than 1, then the series diverges. So what does this remind you of? What do parts 1 and 2 of the ratio test remind you of? The fact that if the ratio in the limit is L, that's less than 1, the series converges. And if the ratio is greater than 1, the series diverges. What kind of series does that remind you of? The ratio test, the parts 1 and 2. What does that remind you of? What series do we know where if the ratio is less than 1, or the absolute value of the ratio is less than 1, the series converges, and if the absolute value of the ratio is greater than 1, the series diverges? That's right, Taj, a geometric series. That's right. So what this ratio test is really saying is, if the terms of the series act like the terms of a geometric series, then eventually, then we can say, we can make a statement about convergence or divergence of the series. That's what this ratio test is really. This is why it works. You're basically, this is why it can work. Now, it doesn't work all the time, but it will work some of the time. And by the way, the third statement there says that the ratio, if the limit of the ratio, or the limit of the absolute value of the ratio of the terms of the series equals 1, then the ratio test is inclusive. So sometimes students like they like the ratio test usually, and they like using it a lot. But in fact, it doesn't work all the time. And those other convergence tests you've learned are equally helpful. But that being said, let's go back to our example here. One moment. No, that's not it. Hold on. Hold on, everybody. Yeah, I brought up the wrong thing here. Hold on. We will take our break soon, but I want to just get this problem done. So problem like this series B here, we're gonna use the ratio test. So let's get to the solution. Here we go. Okay, so for this series, none of the previous 2 tests we learned, I'm sorry, let me say that right. For this series, none of the previous tests we learned can be easily used to establish convergence or divergence of this series. Therefore, let's try the ratio test. So let the nth term of the series be as you see it. So, I mean, well, how am I getting that? Again, if I, let me just write something here. Here's the series. Here's our series. So this is the nth term of the series, and that's what we have here. So now we're going to look at the absolute value of the ratio of the n plus first term to the nth term. Let me give you a moment to catch up here. Okay, so here, the nth term is here, -1 to the nth power times n cubed over 3 to the nth. And to get the n plus first term here, all you do is, in the nth term, anywhere you see an n, you replace it with n plus 1. And that'll get you the n plus first term. So we have a fraction divided by a fraction. A fraction divided by a fraction now. Well, remember, if you have a fraction a over b divided by a fraction c over d, that's going to equal the top fraction times the reciprocal of the bottom fraction, right? That's one of those basic rules that you learned. So that's what we're doing here. With this here, 3 to the nth power divided by -1 to the nth power over n cubed, that's the reciprocal of the bottom fraction. And I have to simplify this expression, right? We have to simplify this expression. And it's always easier to simplify if we put like terms together. So basically what we're going to do here is we're going to group together like terms. So, you know, -1 to the n plus first power and -1 to the nth power, I have those here. I'm just reordering the terms. And then the 3 to the nth power here and the 3 to the n plus first power here, I just put that here. And then the n plus 1 cubed and n cubed, I just put that over here. So this is going to make it easy to simplify. Are there any questions so far? All right. All right, well, let me clear a little bit of this out. One moment. Okay, so let's see here now. So -1 to the n plus 1 power divided by -1 to the nth power. What's that going to equal? If you have -1 to the n plus first power divided by -1 to the nth power, I want to make this nice. The bases are the same, so what do you do with the exponents? Okay, Ange, good. So you're going to subtract the exponents. So n plus 1 minus n. And that's going to give you -1 to the first power. So this is -1, just -1, right? Let's look at this part, 3 to the nth power over 3 to the n plus first power. Okay. 3 to the nth power divided by 3 to the n plus 3 to the power n plus 1. Well, you could think of that as 3 to the nth over 3 to the nth times 3 to the first power, right? So what happens is the 3 to the nth power simplify out, and you're left with 1/3. So this is just going to be 1/3. How many kind of like doing it this way when they do work with fractions, like this kind of approach, as opposed to subtracting exponents? Does anybody do it that way? Okay, Ange likes that way. All right, all right. Well, so now the n plus 1 cubed over n cubed, that part there. And I'm writing this because we're going to be moving to the next page. This here can just be thought of as n plus 1 over n cubed, right? So, okay, let's go to the next page and we got to find this limit, right, for the ratio test. So here we go. So the absolute value of the n plus first term to the nth term would then be hold on, that would be -1 to the first power times 1/3 times n plus 1 over n to the cubed power. Well, the absolute value is going to turn the -1 to the first power into a positive, and then the absolute value of that then is just we can drop the absolute values, and we have 1/3 times n plus 1 over n cubed. And we can think of that as 1/3 times n over n plus 1 over n cubed. And then that's going to give us 1/3 times the quantity 1 plus 1 over n to the third power. And if we take the limit as n goes to infinity, that is going to approach 1/3 times 1 cubed. Because 1 over n, as n gets large, 1 over n has to go to 0, right? And so 1/3 is your L value, and that's less than 1. And therefore, by the ratio test, our series, this series, which is somewhat complicated series, is absolutely convergent and hence convergent. Let me give you a moment to copy this. Please let me know if you have any questions, okay? Please let me know. Okay. Um, so who's well, who's feeling reasonably comfortable with what the ratio test is? Who likes the ratio test? Who kind of likes the ratio test? You've seen a lot of tests, right? A lot of convergence tests. It's like different flavors of ice cream, right? And who kind of likes the ratio test? Okay, Javier's liking the ratio test. Yeah, it's pretty cool. The only thing is it can't always be used because sometimes you use the ratio test on a series and you get an L equal to 1. And then it's you can't determine anything about the series. So I'll make one more comment here regarding this. Again, some intuitive thinking, Um, I'm going to go to the next page if everybody's good. Is anybody still copying this page or are we good? Okay. So, you know, kind of what's going on. This series converges. So the later terms of the series, okay, hold on here, I have to, okay, the later terms of the series will behave, they will behave like a convergent geometric series with common ratio of a third. Because remember, L was equal to 3, or L was equal to a third in the ratio test. So this means eventually this series, okay, the series where we have the absolute value of the terms will act like a convergent geometric series with common ratio of third. Well, if that series converges, then our series converges as well by absolute convergence. I mean, that's really what's going on. It's sort of like, you know, I think of it like, you know, you have this rather ugly series, and you would never think that that series behaves like a convergent geometric series with a common ratio of a third. You would never think that eventually that series behaves like a convergent geometric series with a ratio of a third. And I'm saying eventually it behaves like that. But the ratio test establishes that. And so if our series, our ugly series, eventually behaves like that convergent geometric series, then our series has to converge. It's a lot like an analogy. I have an analogy that how many of you have like seen like a movie where in the beginning maybe it's maybe the person seems like a good guy, but then in the end the person is a bad guy. Or maybe let's think maybe it's better for this. Maybe in the beginning let's do it reverse because we have a good series here at Convergence. Maybe in the beginning of the movie the person seems like a bad guy, but then in the end the person became a good guy, like like Darth Vader in Star Wars. How many have seen like movies like that where the bad guy actually is a good guy in the end? How many have? Okay, Javier and Jan and D'Angelo and David understand what I mean. Sure. That's how I look at this series. This series here, I mean, it's not a series that we can relate to too well. But in the end, it's a geometric series which we can relate to, a convergent geometric series. Okay, good analogy. I think that's really a cool analogy for thinking about convergence of a series. But I don't know how many of you, and I'm going to stop the recording here in a moment, but how many of you think, hey, that's kind of a cool analogy? Does anybody? Maybe one person? Okay, thank you, Mario. I appreciate that. I appreciate that. All right, are there any questions before I stop the recording? Okay, I'm going to stop the recording. We'll take a little break here.